Welcome to AI Paper Slop. Today we are tearing into a big one. It's called GigaBrain 0.7, Scaling Embodied Foundation Models to Emerging Capabilities with a Three-System Architecture.
Yeah, and for the ML engineers and, AI researchers listening, here is the immediate, unvarnished core of what makes this paper so significant.
Lay it on us.
GigaBrain 0.7 is a new Vision Language Action Foundation model, a VLA, that just completely abandons those fragmented, multi-stage pre-training pipelines we've been seeing everywhere.
Right.
Instead, it unifies understanding, prediction, and action into this unified three-system architecture, and it trains all three simultaneously in a single stage, which is wild.
Wow, single stage.
Yeah, and it does this by leveraging a colossal data set, like over 37,000 hours of highly heterogeneous robot data. So by fusing a flow-matching action expert with a predictive world model, GigaBrain 0.7 is just significantly outperforming current state-of-the-art models, and that includes P0.5.
Wait, really? Beating Pi 0.5?
Yeah. We're looking at truly emergent generalization across completely diverse robot embodiments. I mean, it's handling both industrial precision tasks and highly unstructured household environments.
That is a staggering claim right out of the gate. I mean, beating Pi 0.5 is not trivial at all.
Not at all.
But, to grasp how it's actually achieving these numbers, we need to talk about the structural bottleneck of current VLA models. Because the established playbook in robotics right now, it basically seems to be forcing a single architectural paradigm to just juggle everything, right?
Exactly.
You take a massive vision language model, you feed it visual and text prompts, and you try to get it to spit out physical robot movements. Why is that approach suddenly hitting a wall?
Well, the wall they're hitting is a fundamental mismatch in data representation. The dominant paradigm relies super heavily on autoregressive transformer architectures, right?
Right, which we know work great for text.
Exactly. We are incredibly good at training those to predict the next discrete token, whether it's a word or an image patch. So the natural instinct was just, well, let's treat robot actions as just another sequence of discrete language tokens.
Sure. Makes sense on paper.
Right. But high-frequency continuous motor control, like managing the precise torque and velocity of a robotic arm in real time, that is fundamentally not a discrete language task.
No, it's continuous physical physics.
Exactly. Yeah. So when you force a single monolithic transformer to handle high-level semantic reasoning, make coffee, while simultaneously calculating low-level drunk trajectories, you create this massive parameter bottleneck. The network is essentially fighting itself.
Okay, let's unpack this, because it sounds like we're taking a system designed to write poetry or analyze spreadsheets, and we're forcing it to act like a cerebellum, right?
Yeah, precisely.
Trying to calculate the exact micro-adjustments needed to not crush a paper cup. So how does GigaBrain restructure this?
They basically tear that monolithic structure apart. GigaBrain relies on three distinct but highly synchronized systems.
Okay.
So System 1 is dedicated entirely to action and control. Instead of predicting discrete tokens, System 1 is a continuous action expert. It uses flow matching, which conceptually shares some DNA with diffusion models.
Right, okay.
And it generates continuous action chunks, so it operates natively in the physical space of the hardware.
Okay, so System 1 is handling the physical movement.
Yeah.
What drives the logic?
That's System 2, the understanding and planning module. This is a vision language model backbone responsible for processing the temporal context and breaking down long horizon instructions.
Did they use an off-the-shelf VLM for that?
They did, and they did extensive ablations on it. They tested Quinn, Gemma, but they found that Palagia 2, specifically the 3 billion parameter version, was vastly superior for this dual stream setup. It gave much better alignment between the visual inputs and semantic task descriptions.
Oh, interesting. And the third system?
Finally, we have System 3, which is prediction and evaluation. This is a predictive world model. Its entire job is to anticipate the future visual states of the environment, generating what they call subgoal images.
Oh, like predicting the future visually.
Yeah, and simultaneously estimating state values to constantly evaluate the task progress.
I am looking at this three-part structure, and, the biomimicry is just hard to ignore. It really sounds like they've engineered a synthetic brain.
It really does.
Like, you have System 1 acting as the reactive physical nervous system, firing the continuous muscle movements. System 2 operates like the conscious language-driven frontal lobe. And System 3 acts as the internal simulator, literally dreaming or visualizing the physical consequences before the body even moves.
That is a perfect analogy.
But here's the technical hurdle I'm struggling with. If you have these three massive specialized systems running simultaneously, how do they actually share information? Because if you just dump all their parameters into a shared hidden state, wouldn't you just recreate that exact same bottleneck we were just talking about?
Yes, and that is precisely the trap they avoided. The communication between these three systems is not happening through some massive soup of uninterpretable hidden states.
Oh, thank God.
Yeah, they communicate through highly structured, explicit interfaces. There's a semantic interface, a visual interface, and a value-based interface.
Break down how those specific interfaces function in practice for me.
Sure, so System 2, the understanding engine, outputs high-level subtask descriptions. That's your semantic interface. It just passes explicit language conditioning downstream.
Got it.
Then System 3, the world model, generates an actual predicted future image of the goal, along with a scalar value that represents the progress. Those are your visual and value interfaces.
So they are discrete, interpretable outputs.
Exactly. And then System 1, the action expert, takes these explicit representations, the text string, the subgoal image, the value score, and uses them as conditioning variables for its flow mapping process. Because they're passing concrete representations, the systems remain totally decoupled.
That is incredibly elegant. So you aren't forcing the motor control network to learn the abstract definition of a coffee cup from scratch.
Nope.
You simply hand the motor system a synthesized image of the coffee cup being grasped and tell the flow matching system, calculate the physics required to make the real world look like this picture.
That is the exact mechanic at play, but engineering a tri-system architecture is only half the battle, right? To train specialized components to communicate that seamlessly, you are completely reliant on the underlying training corpus.
The data.
Exactly. If the data is too narrow, the systems just immediately overfit to a specific robot arm. And if it's poorly structured, you get catastrophic interference, where learning a physical task causes the model to basically overwrite its language capabilities.
Which brings us to the scale of the dataset. The paper cites over 37,000 hours of heterogeneous robot data. I mean, for anyone who has worked in robotics data collection, that number is almost absurd.
Yeah, it's massive. To be exact, it's 37,256.98 hours of data spanning 16 entirely different robot morphologies.
What?
Because the scaling problem in embodied AI has always been the hardware variance, right? One data set has a 6 degree of freedom arm, another has a bimanual robot with 7 degrees of freedom. So to handle this, the GigaBrain team engineered a massive processing pipeline to standardize every single trajectory into the Lee robot v3.0 format.
Okay, but how does that 37,000 hours actually break down? Because I imagine it can't all be high-quality, teleoperated robot data.
Right. It's a heavily engineered mixture. 55% of the corpus is real, physical robot data, mostly from platforms like Maker H01 and AgileX. But the real leverage comes from the secondary data sources.
Like what?
So 20% is UMI data. UMI stands for Universal Manipulation Interface. These are near-hand human demonstrations collected using a specialized handheld gripper tool.
Oh, so it captures fine human dexterity without an expensive robot.
Exactly. Then another 7% is ego, or first-person human video.
Wait, what is the specific value of the ego data? If there's no robot arm in the video, how does that help the action expert?
Well, ego data provides profound priors for human intent and spatial attention. It teaches the world model where humans look and how they approach an object before they interact with it.
Oh, that makes sense.
Yeah, and then they supplement this with 11% world model generated synthetic data and roughly 4% pure physics simulation data. And crucially, layered on top of all of this, they include 271 million vision language model samples.
Like general image captioning stuff.
Exactly. Image captioning, visual Q&A, that kind of thing.
Okay, wait. If you are jointly training 271 million pure language and vision text pairs alongside tens of thousands of hours of grinding physical robot actions, how does the model not collapse?
Yeah, it's a huge risk.
Because if the action expert is updating its weights based on flow matching errors, and those gradients are flowing backward into the VLM backbone, wouldn't the VLM just override its general intelligence? It feels like teaching a brilliant scientist to dig ditches, and in the process, they just completely forget how to do math.
You are describing the exact mechanism of catastrophic interference. If you allow the flow matching loss from the physical actions to backpropagate with full force into the VLM backbone, those delicate semantic representations get totally obliterated.
Right.
The VLM might learn to track the spatial coordinates of a red pixel perfectly, but it entirely forgets the abstract concept that the red object is an apple.
Here's where it gets really interesting.
Yeah.
How do they isolate the language center from the physical training?
They implement a mechanism they call soft knowledge insulation, or soft KI.
Yeah, looking at the math behind soft KI, it functions almost exactly like a mechanical shock absorber sitting between the physical action system and the cognitive language system. But how does that attenuation actually work at the gradient level?
It's actually brilliant in its simplicity. They allow the flow matching gradients to backpropagate fully through System 1, so it learns the precise physics of the movement. But the moment those gradients cross the threshold and hit the VLM backbone in System 2, they are multiplied by an attenuation coefficient.
Oh, I see.
It's just a fractional scalar that shrinks the gradient.
So the VLM still feels the error from the physical mistake, but it's mathematically muted. It's like a gentle nudge to the weights rather than a catastrophic rewrite.
Precisely. It allows for controlled, gradual adaptation. The VLM learns to align its visual and semantic representations with the realities of embodied control. But the primary supervisory signal keeping its semantic weight stable is still coming from the next token prediction loss of those 271 million general vision and language samples.
So soft KI basically ensures the backbone retains its broad intelligence while evolving into this highly specialized contextual engine.
Exactly.
Okay, so that solves the data clashing problem. But having properly formatted, insulated data is only the prerequisite. The way GigaBrain actually ingests this massive corpus represents a stark departure from the current meta. Let's look at the training paradigm itself.
Yeah, if you look at architectures like Pi 0.5 or Gemi Robotics 1, they rely heavily on multi-stage pre-training pipelines. The standard procedure is to pre-train the vision language model first, freeze those weights, and then train the action expert in a separate stage.
Right, keep them isolated in time.
Exactly. Or some teams pre-train the entire model on discrete action tokens and only introduce flow matching during a final fine-tuning phase. GigaBrain discards all of that. They execute a massive, unified, one-stage VLA pre-training framework.
They are jointly optimizing the next token prediction and the flow matching entirely simultaneously. That has to be an absolute nightmare to balance, but if they pull it off, it explains why the model doesn't have that out-of-sync behavior we often see.
It definitely creates a much tighter coupling between intent and action, but, pre-training on a static data set, no matter how large, has a hard ceiling. Pre-training is basically just imitation learning. It works beautifully until you deploy the policy onto a real robot. The moment the robot makes a slight error and drifts into a state that wasn't in the training data, the errors compound and the policy fails.
And historically, the only way to fix that out-of-distribution drift was to bring humans back into the loop, manually teleoperate the robot to correct the mistake, and add that new data back into the pile, which is incredibly expensive.
Yeah.
How does GigaBrain break that cycle?
They introduce an experience-driven reinforcement learning loop. And this is where System 3, the predictive world model, just completely changes the paradigm.
Okay.
After the initial pre-training, they deploy the VLA on physical hardware and allow it to collect offline rollout trajectories. Crucially, they collect both the successful attempts and the failures. Then, instead of a human grading those rollouts, System 3 steps in as an automated value progress discriminator.
Wait, so System 3 watches the telemetry of the robot's attempt and assigns it a mathematical score based on how close it got to the goal state.
Yes. They utilize an RL algorithm called advantage-weighted regression, or AWR. In that objective function, they take the value estimates generated by System 3 and use them to weight the training updates.
Okay, it sounds like the model is essentially sitting down and watching its own blooper reel, right? It's reviewing footage of itself failing, but using System 3 to analyze the nuances of the failure.
That is a highly accurate way to frame it. Because of the advantage-weighted regression, a complete failure isn't just discarded as useless data.
Oh, interesting.
Yeah, if a rollout failed. But System 3 recognizes that the first half of the trajectory, like the approach and the initial grasp, showed high progress toward the goal. That specific segment of the blooper reel receives a heavier training weight. The model literally isolates the useful behaviors embedded within its own mistakes.
By extracting those partial successes from its own failures using System 3's predictions, the model is bootstrapping its own physical competence. It completely bypasses the need to have a human sitting there grading trial and error.
It creates a closed-loop system of continual rollout, automated correction, and policy update. The sample efficiency gains are massive.
Okay, we have unpacked the underlying machinery, we have a tri-system architecture, we have 37,000 hours of standardized data, soft knowledge insulation, one-stage training, and a self-scoring RL loop. The theory is airtight. But does this architectural complexity actually translate to superior performance when loaded onto physical hardware?
The empirical results are incredibly compelling. They deployed GigaBrain across multiple platforms with the most rigorous testing on the Agilex Piper and their Maker H01 platform.
And how did it handle out-of-distribution testing? Stuff not in the dataset.
That's the best part. The most illuminating result regarding the three-system architecture comes from their Ablation study on the gift wrapping task.
Gift wrapping is a notorious benchmark.
Yeah.
You're dealing with wrapping paper, which is highly deformable. It crinkles, it tears, it never folds the same way twice. For a traditional robotic system, a deformable object is a total nightmare scenario.
It is arguably the ultimate test of continuous state estimation. So the researchers ran a baseline test using a truncated version of GigaBrain, just System 1 and System 2. They completely disabled System 3.
Okay.
Without the predictive subgoal images and the value conditioning from the world model, the success rate on the gift wrapping task was 0%. Absolute failure across the board.
The model literally could not comprehend how to manipulate the paper without the world model guiding it.
Correct. But when they re-engaged System 3, feeding those predicted future visual states into the flow matching action expert, the success rate immediately spiked to 80%.
Wow, 0 to 80.
And the average task completion time dropped by a full 10 seconds. We see the exact same emergent capability in their clothes folding benchmarks. The model demonstrated the ability to fold unseen garment instances like crumpled shirts, starting from highly unstructured random initial states guaranteed to be absent from the training data.
So what does this all mean? The mechanics of folding an unseen crumpled shirt are just mind-bending to consider computationally. A crumpled shirt represents a functionally infinite state space. There's no mathematical possibility that the 37,000 hours of training data contain the exact topographical map of every single wrinkle of that specific shirt.
No, absolutely not.
How does the injection of System 3's predictive subimages allow the physical hardware to navigate a topographical reality it has never encountered?
The key is that System 3 is not simply functioning as a pixel memorization engine, right? It has internalized the fundamental physics of the physical world. Even if it hasn't seen that exact wrinkle, the predictive world model understands the underlying physical rule. If I apply tension to this fabric vector, the adjacent fabric will smooth out.
Ah, I see.
So System 3 leverages that physical intuition to generate a predictive subimage of what the shirt should look like 2 seconds into the future, a partially smooth, slightly more structured shirt.
It's essentially creating a visual North Star for the action expert.
Exactly. The flow matching policy in System 1 no longer has to solve the infinite state space of the crumpled shirt. Its only job is to calculate the continuous motor torques required to make the current reality in front of the camera match the predicted reality generated by System 3.
So the infinitely complex physics problem is collapsed into a step-by-step visual roadmap. The world model imagines the immediate future, and the action policy pulls the physical body toward it.
Beautifully said, yes.
It's using a synthetic imagination to physically guide its hands through an unknown environment. It is a profound shift in how we approach embodied AI, and it forces a much larger conversation about the ultimate trajectory of this technology.
It really does.
If System 3, this predictive world model, is already capable of generating localized physical futures with enough fidelity to successfully condition a robot's flow matching policy, what is the logical endgame here? We're analyzing version 0.7 today. Project this forward to version 3.0 or 4.0. If these predictive world models scale to the point where they perfectly simulate physical reality, calculating friction, gravity, mass, deformable dynamics,
the implications are paradigm shifting for the entire field of robotics, because the immediate question becomes, at what point do we entirely cease the collection of physical robot data?
Exactly.
If a world model possesses a flawless internal representation of physical dynamics, future VLAs might not require real-world teleoperation at all. They could simply dream their entire physical training regime, running millions of simulated trial and error loops inside a hallucinated internal environment before ever being downloaded into a physical chassis.
We are rapidly approaching a threshold where the primary bottleneck is no longer the agonizingly slow collection of physical data, but rather the computational fidelity of our synthetic world models.
Yep, the simulation becomes reality.
The completely internally generated curriculum, where the AI masters the physical world before it even possesses a physical body. That is the reality that architectures like GigaBrain are accelerating us toward. We've transitioned from the rigid token prediction of early models to a fluid, dreaming, tri-system synthetic brain. The convergence of perfectly predictive world models and continuous physical robotics isn't just theoretical anymore. As the data in GigaBrain 0.7 proves, it is already operating in the real world. That's all we have for you today on AI Paper Slop. Thanks for joining us.